Hi everybody, this is lecture 10 and today we'll tell you about the chain rule and the gradient vector. So let's get started. So before we I tell you about the chain rule proper, let me prepare the ground a little bit. So let's say we have a function of three variables, so f of x, y, and z. So the observation I'd like to make is this, that to a first order approximation, so let's say I look at the value of f at a point, and then I just change, so at point x, y, z, and then I change the point a little bit. So I change x by a little amount, y by a little amount, and z by a little amount. So what happens to f? The answer is given by this approximation. So if I look at the value of f and then change at a point, then change the point a little bit, the change in f to a first order approximation, to a good approximation, is given by the x partial of the function. So the x partial. So here I'm using the notation f sub x for df dx. So it's the x partial multiplied by the change in the x coordinate of the point plus the y partial times the change in the y coordinate of the point plus the z partial times the change in the z coordinate of the point. Okay, so this is this approximation is going to be our starting point today. I won't prove it for you. Let me say that you can use this going forward. It's true for all ordinary functions. So technically, what you need, the conditions that ensure that this holds are, for example, that the function f has all three partials, and the three partials are continuous functions of x, y, and z. So if all partials exist and they're continuous, then this approximation is true. So we're going to take that for granted. Oh, I said three partials, and then this reminded me what all I'm going to say today works in two variables as well as in three variables. And in fact, it works with any number of variables, but for concreteness, we'll be working either with two or three. But please bear in mind that you could have more variables as we move forward. Okay, so here's going to be the setup for the chain rule. So we're going to assume that x is f changes with the variables x, y, and z. And now let's assume that x, y, and z depend on another variable. Let's call it t. So let's say that x is a function of t, y is a function of t, and z is a function of t. So f changes with x, y, and z. X, y, and z in turn change when t changes. And the question that the chain rule answers is, how fast does f change when t changes? So what's the rate of change with f with respect to t? So, and the answer is this. So I'm just going to write it down. It's the x partial times, so you first see how fast f changes with x, right? That's the x partial tells you how fast f changes when x is fixed. Then you multiply that by the rate of change, the speed with which x changes. And then you add, so that's the contribution coming from x. There's the other contribution coming from y, similar term, and also a contribution coming from z. So if t changes, x, y, and z are going to change, and each of these changes, so the change in x is going to come together with the x partial. The change in y comes together with the y partial of f of the function, and the change in z comes together with the z partial. So this formula, this expression here, for the derivative of f with respect to t, in terms of the derivative of f with respect to x, y, and z, and the derivatives of x, y, and z in terms of t, so this expression is called the chain rule. So it's similar to the chain rule so it has as a special case when you have a single variable. This is saying df dt is df dx times dx dt. That's the usual chain rule from single variable calculus. So what I'm really saying here is that if you have more variables, you just add a contribution for each variable. So So I want to show you an example of this, but before I proceed, just so this doesn't seem this box I asked you to take for granted, just so this pill doesn't seem too large to swallow, let me try to convince you that it at least is compatible with something else that you guys know. So let's say, so what happens to this formula when I'm changing the point, so when I'm changing x, y, z to a different point, y and z stay the same. So if I fix y and z and only change x, then delta y and delta z are 0. So these two terms go away. And then I'm saying that the x partial is approximately the change in f divided by the change in x when y and z are fixed. So this is true by definition of the derivative, of the partial derivative with respect to x, because you're fixing the other two. So this first part, so this is all to say that this formula shouldn't be too surprising. But in any case, we're going to take it for granted, and we'll actually be working with this consequence of the formula. We're going to be, from now on, be working with the chain rule rather than the formula. But I should note that these two look similar, and it's not a coincidence, right? If you just divide this formula here by delta t, and then let delta t go to 0, you're going to get the derivative of f with respect to t on the left, and then these delta x times delta t just becomes this derivative, and similarly for the other terms. Okay, so let me show you how the chain rule can be used in a simple case. So example. So what I'm going to do now, you could do, without using the chain rule, but the point is that using the chain rule gives you another way to do it, and it helps to checking that you get the same answer helps build confidence in the chain rule. So here's the example. Let's say the function is x squared times y plus z, and that so f depends in x, y, and z in this way, and then let's assume that x, that x, y, and z are these functions of t. So x is just the function t, y is, so y of t is just e to the t, and z is just sine of t. Okay, so we want to know the derivative of f with respect to t. So we absolutely could do this by just plugging these formulas. So just plug the formula t wherever I see an x in the formula for f, plug e to the t where I see y, and plug sine t where I see a z. I could just plug everything in the formula for f, then f would be expressed in terms of t, and then differentiate by using the composition and product rules and so on. And I would get the correct answer. Here's another way to do that. Just use the chain rule. So the x partial, in this case, is if I differentiate f with respect to x, I get 2 times xy, and then multiply the x partial, so that's the x partial, multiplied by dx dt, that's 1, plus the y partial of f, that's x squared, times dy dt, so the exponential is its own derivative, so that's again e to the t, plus the z partial of f, that's 1, times the derivative of z with respect to t, that's cosine t. Okay, so we're almost done to get this derivative. So I think it's preferable to have the answer either in terms of just x, y, and z. In this case, it's not possible, or in terms of just t. So let's just write everything in terms of t. I'm going to get 2 times x times y, that's t e to the t, plus x squared times e to the t, so that's t squared e to the t, plus cosine t. Okay, so there you go. This is just to show you that the chain rule is doing something really concrete for us, helping to differentiate the composition. F really, basically the composition of f, which depends on x, y, and z. So f is a function of x, y, and z. X, y, and z are functions of t. It helps you differentiate the composition where you express f in terms of t. So before we move on, I'd like to make a comment about this example, which I think is helpful when doing one of the homework problems for this week, and has appeared in exams in the past at UW. So let me make that comment. So here's the observation. So remark. Let's make this really official. So we have an official remark. So let's say I want to know. So to know the derivative of f with respect to t for a specific value of t. So let's say t equal to 1. I need two things. Oops, not need. Need. We need two things. So we need the partials of f and we need the derivatives of the variables with respect to t. Right, so so far so good. So we need these derivatives and we need these partials. Right, that's clear from this formula. To compute this, I need the partials and the derivatives of the variables. But we actually don't need to know the derivative of the variables for all values of t. And we don't need to know the partials at all points. It actually suffices to know the derivative so for t equal to 1, right? So I just need to know the derivative at time t equal to 1. So these derivatives of the variables. And right, so here's what I'm saying. If I have a little, so let me try to make this more concrete. So let's say we have a function. So our function of x, y, and z is the temperature in space, right? And there's a little bug flying around. And x, y, and z of t is the position of that bug at time t, right? So we know that at time. So if I want to know, we want to know df dt at time 1. So we want to know how fast the temperature is changing for that little bug at time equal to 1. Right? The bug is changing its position, and because the temperature depends on the position, it's also changing its temperature. So we want to know how fast that change is coming about. Now, so what I'm saying is, if I want to know how fast the temperature is changing for the bug at time t equal to 1, I need to know where the bug is. I need to know how fast the temperature is changing with position at that position, where that bug is. So here I'm saying that in the previous example, so to kind of jump between two examples, my apologies there. If I want to know, if I just want this derivative when t is 1, I need to know these values when t is 1, right? So I need to know, I need these derivatives at the point x of 1, y, y1, z of 1. So coming back to the example of the bug, so I need to know how fast the temperature is changing with position at the position of the bug, and I need to know how fast the bug is moving. And if I know where the bug is, how fast it's moving, and how fast the temperature is changing with position, what's the rate of change of the temperature with position in all three directions, I'm able to reconstruct the rate of change of the temperature for the bug with time via the chain rule. But the crucial point is I don't need to know, I just need to know how fast the bug is moving right now. I don't need to know how fast it was going yesterday or how fast it's going to be tomorrow. I just need to know its speed right now, and I just need to know how the temperature changes with position at the position of the bug, where the bug is right now. I don't need to know how fast the temperature changes with position at other points. Okay, So let me show you. So still to keep building some trust, I want you guys to really trust the chain rule. To help do that, I'd like to show you another application where the chain rule gives you an answer that you guys already know is correct. So here's that application. So we can use the chain rule to recover the product and quotient rules from single variable calculus. Let's see that happening. Okay, so here's the setup. We want to differentiate f. So we want to differentiate the product of two functions, u and v, and where we know that u and where u and v are functions of t. Right. So here f doesn't depend on x, y, and z. X depends on u and v in turn depend on t. We want to know how fast f, the product of u and v, changes with t. And here's what the chain rule tells us. So d of uv dt, so the derivative of the product is equal to the u partial, so that's the u partial of f times du dt, plus the v partial of f times dv dt. Now f is the function u times v, so the u partial is just v. And the v partial of f is just u, and you multiply that by dv dt. Voila, you just differentiate one and multiply by the other, and then differentiate the other and multiply by the one. So that's the familiar thing. The other example is so if we instead of u times v we look at u divided by v, but still u depends on t and v depends on t, the derivative of the quotient. So that's g sub u, so the u partial of g times du dt, plus g sub v times dv dt. Now, in this case, so the u partial of g is just 1 over v, and the v partial of g is, so we have u times v to the minus 1. If I differentiate that, I get minus v to the minus 2. So minus u divided by v to the minus, v squared. Right, and if you put this with a single denominator, you'll recover the usual formula. Okay, so one more comment I'd like to make is that the chain rule works with more variables. So before going to the gradient vector, let me make a final remark about the chain rule. So it works with multiple variables. Chain rule the chain rule we've had so far involved multiple variables, x, y, and z, for example. But here, I mean to say that x doesn't have to depend on a single variable t. It could depend on two variables, u and v. Right. So, for example, let me do the case with two variables. So let's say f is a function of x and y, and that x is a function of two variables, u and v. Y is a function of two variables, u and v. Right, so for example, u could be r from polar coordinates, and v could be the theta, the angle from polar coordinates. And then it would be a very fair question to ask. So how fast does f change with r? Or sorry, and we're working in general here. So how fast does f change with u? Given that we know how fast f changes with x and how x and y change, how f changes with x and y, and how x and y change with u and v. So this we don't need a new formula here. We can just use the single variable chain rule from before, because this partial here, when you take a partial derivative, you fix. So in this case, we're fixing the variable v and taking a regular derivative with respect to u, right? So, and this is just notation for fixing v and taking a derivative with respect to u. So let's just take this derivative with respect to u. According to the chain rule, you get the x partial times the derivative of x with respect to u with v fixed, so that's denoted by curly derivative like this, du, dx, du, plus the y partial of f times dy du for the same reason. We're fixing the variable v and taking a derivative of y with respect to the other one. So that's a partial. And similarly, if I want the v partials of f, let me move this down so things don't look too crammed. We get f sub x times dx dv plus f sub y times dy dv. And as I said, this works with polar coordinates. All right. So this is what I had to say about the gradient. Let's move on to our next subject. This is what I had to say about the chain rule. Let's move on to our next subject, the gradient vector. So this is like really, I'm going to make some really useful observations here, right? So these are, so in machine learning, you often hear about gradient descent, right? You have a model that depends on a bunch of what are called hyperparameters, a bunch of variables, and the error depends on these hyperparameters as well. And you want to continuously improve your model so as to decrease the error. So you want to change the parameters, the so-called hyperparameters, to decrease the error. And the way you do that is you take a gradient, you compute the gradient of the model, so that's a kind of derivative with respect, a gradient of the error with respect to these hyperparameters, and that vector tells you how to change the hyperparameters to decrease the error. Anyway, this probably would have made more sense after I told you what the gradient is, but I hope to have given you an idea that this what I'm about to say is important. So the gradient is here. So it's a derivative of a function with several variables. It's a vector that we build from the function. We just put the x partial in the first component, the y partial in the second component, and the z partial in the third component. So that's it. So the gradient vector is this vector we build from the three partials, using the three partials of the function. So it's really computable. You can certainly evaluate it on most cases. So what I want to do next, and what I want to do with the rest of today, is to explore the geometric meaning of the gradient. Right. So right now I told you what the components of this vector are. I want to focus now on the length of the gradient. But a vector is geometrically, a vector is built of a direction and a length, right, and a magnitude. And I want to explore the direction and the magnitude. So let me give you a theorem that tells you what is the geometric meaning of the direction of the gradient. So here's the theorem. Okay, I'll write it in full for once. So theorem. So the theorem is just a simple statement. It says that the gradient of a function I'll squeeze it up here. So the gradient of f is perpendicular to the level set. F equals a constant. Right? So let's unpack this. first of all, I said gradient vector. It would have been better if I had said gradient vector field, but we're going to talk about vector fields in more detail later. But you should note that we can evaluate these derivatives at several points x, y, z. Each point x, y, z will give me a different gradient vector. But we have a bunch of these, and what I'm saying here applies to all of them. So let's say I'm in 3D. Sorry, I'm in 2D to simplify, to make my picture easier. Later I'll try to draw this picture in 3D. And let's say I take a point and compute the gradient vector there. Right, so this is the gradient, but evaluated at this particular point that I drew in black. Let's say let's say that the value of f at that point is 1. For example, for sake of argument, it could be anything, but let's say it's equal to 1. Right? What I'm going to do now is draw all other points in the xy plane that have this property that f of f at that point is equal to 1. So let's say something like this. Right, so this is the set of points where f is equal to 1. I could, f takes many other values. So for example, what I just drew over here could be the second curve, could be the set of points where f is equal to 2, and so on. So what theorem is saying is that the function, that the gradient vector is always perpendicular to the level set. So a level set of a function is a set. So first of all, a function has several level sets, and so one level set is the set of points you get by looking at all. So f equal to 1, the set of points where f is equal to 1 is an example of a level set. The set of points where f is equal to 2 is another example of a level set. You get infinitely many examples by changing the right-hand side. But any given point lives in the level set. You just look at all other points with the same, where f takes the same value as it does at the given point. And the theorem is saying if I compute the gradient, it's going to be perpendicular to the level set. I should be a little bit more careful. So the level set in principle could be a curved shape. So we do understand what it means for a vector to be perpendicular to another. But what does it mean for a vector, or for example to a line, to a plane? But what does it mean for a vector to be perpendicular to a curved shape? So this, by definition, what I really should be saying is that the gradient of f is perpendicular to the tangent line, to the tangent space, to the level set. Okay, let's so this is a lot to unpack. Let's look at a few examples, or at least a couple of examples. So example number 1, exhibit A, is the function f equals ax plus by plus cz. So a, b, and c are constants. So a level surface. So this is a function of 3 variables. Let me note this, that when you have 2 variables, so if you have 2 variables, I hope I didn't confuse you guys. So when you have 2 variables, the gradient is you don't include the z variable. You don't include the z partial. So the gradient has 2 components in 2D, 3 components in 3D. In level sets, if I impose the equation f equals a constant in 2D, I will go from so the set of all points in the plane that satisfy this equation, f equals a constant, will give me a curve. But in 3D, if I impose an equation, I will get a whole surface of points where f is equal to that given constant. So in 3D, we talk about level. So in general, we talk about level sets. In 2D, we talk about level curves. In 3D, we talk about level surfaces. Okay, so in this situation, the level surface. So that's the set of all points where, so all points x, y, z, where ax plus by plus cz equals a constant. Let me call that constant d. So this set is a plane. And right, this is a familiar sort of equation. This is a plane. And what the theorem is telling me is that the gradient vector is perpendicular. The gradient of f, so the gradient of this function here, is perpendicular to this plane. So the gradient is a normal to the plane. So with normal, gradient of f, and that's, so in this case the gradient is, so the x partial here is just a, the y partial is b, and the z partial is c. Right, so we're coming back to something I told you when we were discussing the example of the tetrahedron, that if I have a plane like this, ax plus by plus c equals d, you can just, by looking at the equation, you can tell the normal vector of the plane just by looking at the coefficients. So this is coming back from this. This is a consequence of this theorem that I stated in the previous slide. It works, the theorem, even though the picture I drew in 2D, the theorem works in 2D and in 3D. Okay. So let me try to give you an idea why this works. Why this is true without resorting to the theorem. So let me look at the left-hand side. The left-hand side is like a dot product of two vectors. It really is the dot product of two vectors, right? The one vector is ABC, and the other vector is XYZ. So this plane, so any plane consists, and in particular this one, so this plane consists of all points XYZ, which such that the dot product of that point with the position vector of that point with ABC is equal to D. Okay, so let's try to understand this statement in the case where D is 0, right? And I claim that when D is 0, so when the right-hand side is 0, the statement that this plane, the normal vector for the plane is ABC, this statement is okay when D is 0, right? Just because the equation of the plane is telling me we're looking at all points XYZ with dot product with ABC equal to 0, right, if D is 0. Looking at all points, so dot product being 0 is the same as saying the two vectors are perpendicular. So the very definition of, when D is 0, the very definition of the plane is telling me that it consists of all points XYZ which are perpendicular to ABC. In other words, the normal vector of the plane is ABC. Now, if I have a non-zero right-hand side, so linear algebra comes to the rescue. So we're looking at the set of solutions to an inhomogeneous linear equation. So they are all, you can get, so that's like a plane. So basically, so here's the brief situation. We have the set, so you have some plane going through the origin. That's the set of solutions to the homogeneous equation. For the unhomogeneous equation, all solutions are like translates of solutions to the corresponding homogeneous equation. So both planes have the same normal vector, right? So the set of solutions to, so I'm saying that the normal vector of ax plus by plus c is equal to D, that is the same as the normal vector of the same plane of the homogeneous plane, the corresponding plane through the origin where D is 0. Okay, so let me show you another visual example of the theorem, this time a 2D example. So here's the 2D example. So our function f of xy is x squared plus y squared. Okay, let's see what the level sets look like. So here's the xy plane. So for example, what's the level set occurs with level 1, right? The set of level 1 for this function is the set of all points where x squared plus y squared equals 1. That's the circle of radius 1. So let me draw it here. Okay, this is the level set where f is equal to 1. Good. Now, for example, what about the level set where f is equal to 2? So if the level set course with value 2, with level 2 is x set of all point solutions to x squared plus y squared equals 2. That's the circle of radius root 2. So that's kind of here. Okay, my circles aren't looking as good today as they normally do. But this is 1 and this is 2, and root 2 is kind of in between. So you see that the level sets are concentric circles. Now the gradient vector for the function f of xy equals x squared plus y squared is, so let's take a point here in one of these circles. So this point has position vector x comma y, right? The point has position x comma y. The gradient, I claim, is 2 times this position vector. So the gradient of f, so the x partial of this function is 2x. The y partial of this function is 2y. So that's 2 times, so the gradient evaluated at a point is 2 times the position of the point. So you can see that the gradient really is, the gradient is radial, whether circles are I mean, a ray meets each circle about the origin with an angle of 90 degrees. I hope that can be, either you can think of this as a theorem in geometry, or you can say it's visually very believable. Let's stick to believable. I'm happy to stick with believable for now. So the theorem. So in this example, you can see that the theorem, what the theorem tells us, is also true. So that's it. I mean, you should believe in this theorem. Let me now show you a sort of problem that you can solve using this theorem. So an application. So I will even so let's do this application. Okay. So here's something we can do using that theorem. So let's believe the theorem that the gradient vector is always perpendicular to the level sets of the function. Let's believe this is true for any function. So we've seen this working in these two examples, in the case of a plane or in the case of a circle. So let's believe this is true in general and use that to do something interesting. Okay, so our job is to find, and this is the sort of thing you do in homework. So our job is to find the tangent plane. So find the tangent plane of the surface with the following equation. So x squared plus y squared minus z squared equals 4 at the point 2, 1, 1. Okay, so so this equation, we don't need to. So our job is to find the tangent plane of this surface at the point 2, 1, 1. So first of all, so this problem we can solve without drawing the surface. So we don't have to worry about that picture. Even though this does have a nice picture, I will resist telling you about it. telling you about this geometric shape. Let's just make sure that the problem makes sense. So is it true that this point belongs to this surface? Is it true that if x is 2, y is 1, and z is 1, then this equation is satisfied? Yes, right, because 2 squared plus 1 squared minus 1 squared is equal to 4. Okay, good. So the problem makes sense. Now let's find, but we should ask ourselves, why is this, what's the relationship between this application, this problem, and what we've seen before? And the answer is that the surface, so we're looking at the level set, so this surface is a level set f equal to 4, where the function is x squared plus y squared minus z squared. Okay, so any surface, so surfaces that are given to us as a set of solutions to an equation, they're all level sets, right? You can always put them in this framework. Now the gradient, so the gradient is the key here. So the gradient of this function, so this gradient is normal. The gradient of this function is normal to the surface, right, to this level set. And as I said, it means it's normal. The gradient is perpendicular to the whole tangent plane. So this gradient is the normal to the tangent plane. Let's compute it. So the gradient is 2x, 2y, right? The x partial here is 2x, the y partial is 2y, the z partial is minus 2z. So at the point 2, 1, 1, the vector we get is 4, 2, negative 2. So this vector is normal to the surface at that point, which really means it's normal to the tangent plane at that point. But now, if I know the normal vector to the tangent plane, I know the equation of the tangent plane, right? So the tangent plane, so I know its normal vector, right? Here it is, and in the normal vector, I can read the coefficients of the tangent plane. So that's 4 times x plus 2 times y, minus 2 times z equals something. Right? That's the right-hand side doesn't come from the normal vector, but I know the tangent plane has this shape. And how do I figure out the right-hand side? Well, I know the tangent plane has to go through the point 2, 1, 1. So this equation must be true when x is 2, y is 1, and z is 1. So this tells me that the right-hand side must be 8. Right, because so 8 comes from the fact that the plane contains 2, 1, 1. Okay, so this feels like enough for a lecture. So I'm going to stop right here. In the beginning of next lecture, I will tell you guys why this theorem is true. It's going to be a nice, it's kind of tricky, but it's a nice exercise in pure math. I won't tell you just about this. I will also explore that the meaning of the length of the gradient and rate of change, and which relates to that brief application to that application to machine learning that I mentioned at the beginning of the lecture. Okay, so that's it for today. Thanks for listening, and I'll see you guys next time.